afternoon in Europe.
Mm-hmm. Okay, I think we can officially start. There are a lot of people here. We start the first talk by Alexei Prokutin in place of Daniel Pitonyak, who is going to talk about the global analysis of single transverse spin asymmetries and the impact of the EIC on the tensor charge.
Yeah, thank you, Marta. Thank you for the opportunity. Good morning and good afternoon, everybody. Yes, I'm Alexei Prokutin from Penn State Bergson Jefferson Lab, and I will give this talk on behalf of Daniel Pitonyak, who, due to family emergency, couldn't give it. And it is about our work on global analysis of single spin asymmetries and the impact of the extraction of tensor charge through the future EIC data. If we talk about TMDs and our analysis concerns TMDs, we can place them on this table as a function of quark polarization and nucleon polarization. There are 8 functions in total at leading twist. 2 of them are naively T-odd, so they change sign from Sidis to Drell-Yan. And in particular, the interesting one that I'll talk about is Siever's function. It generates the single spin asymmetry sine phi h minus phi s asymmetry in Sidis by coupling to unpolarized fragmentation D1 and sine phi symmetry in Drell-Yan by coupling to anti-quark or quark distribution function and the other unpolarized proton in Drell-Yan. Siever's function can be related to the so-called twist-free matrix element or Twist-Torment function, which is the quantum mechanical correlation between multi-parton states in the wave function of the nucleon, and it is related in TMD formalism also to the Sudakov form factor, and its BT dependence is defined by these factors here. If we integrate over KT, then in collinear approximation, there are 3 functions, F1, helicity, and transversity, that define the spin structure completely of the nucleon. And 4 functions corresponding to the transversely polarized nucleon are chiral odd, and they need to couple to other chiral odd functions in order to produce cross sections that can be measured. It turns out that transversity is perhaps the least known one and extremely interesting, as this combination here, the difference between quark and anti-quark transversity integrated over X in the whole region, the first moment of it, corresponds to the tensor charge of the nucleon. And particularly interesting is the isovector combination, the difference between delta U and delta D, which is called GT. It turns out that this tensor charge is one of fundamental charges of the nucleon, and it's important for the beyond standard model studies, for instance, in beta case. And it turns out that processes sensitive to TMDs can play a very important role in these efforts, as was emphasized by papers by Aurore and others, Yamanaka and Lee. It turns out that also tensor charge is an object that can be calculated pretty easily on lattice, and there are many calculations on lattice with very great precision. The latest one by Gupta, Hassan, Alessandro, and Marta participated in those studies in 2018, 2019. So tensor charge is the point of contact between studies of TMDs, studies of beyond standard model physics, and lattice studies. In order to access transversity via TMD measurements, it has to couple, for instance, through Collins function, and then it produces sine phi h minus phi s asymmetry in Sidis. Collins functions can be accessed also in a plus or minus. Their convolution of 2 Collins functions would produce cos to phi symmetry. Again, we can do operator product expansion for transversity TMD and it will go through collinear transversity, the one that is important for tensor charge, and the coordinate fragmentation function can be related via operator product expansion to the twist-free fragmentation function, or this matrix element, which is shown here. A sub n in proton-proton collisions, left-right asymmetry, is a notoriously known collinear twist-free observable, as it only has one measured scale, and it can be described in twist-free formalism by combination of Choose-Terman term due to the Choose-Terman and fragmentation term due to the QQ bar fragmentation function and this additional function H tilde. We studied contributions from both of those terms and found out that the fragmentation term gives the biggest contribution to the observed asymmetry, which is shown here. And it tells you that in principle, the underlying picture of all those single spin asymmetries is within those correlation in the wave function of the nucleon between just one quark and gluon, and so on and so forth, which are the so-called twist-free functions. They can be related to TMDs and operator product expansion. They can be used in twist-free formalism directly. And so in principle, one could take all those data and do the extraction of functions. And that's what we did in this paper that we published in 2020. Here are results of the extraction and comparison of data for semi-inclusive plastic scattering data here, for plus minus data here, A sub n and Jailyan here. Chi-square was very good, it's around 1 or 420 points. We extracted transversity for up and down quarks and compared it to previous extractions. For up quark, it's positive, for down quark, it's negative. We extracted the first moment of series function that can be related to Choose-Terman matrix element. Again, for up quark, it's negative, for down quark, it's positive, and then it is also comparable to the existing extractions. And the first moment of coordinates function that can be related to the twist-free function that describes fragmentation is also extracted for favorite and unfavorite fragmentation. Again, signs are different here, and they are compatible with existing extractions. I'll concentrate on transversity in this very talk here, and let me show you the results of contribution to tensor charge for contribution delta U and delta D and GT here. So our global analysis here is in red and global. If we use only CDS data, then of course we don't have a lot of constraints. So this is ellipse in blue here. We have to add a plus and minus data, of course, then it makes analysis more precise, but only after adding A sub n data. After the simultaneous global analysis, we get a better description, and very notoriously this description here in pink is compatible with the lattice QCD calculations, and you can see also that here our result is compatible with lattice QCD. There is some tension of previous phenomenology with lattice QCD, and looking forward to resolving C and seeing what the issue is. So what we did in our new paper, we generated data for a plus, so for electron ion collider for 7 different energies for EP and E helium-3 polarized. For each energy, around 10 inverse femtobarn was generated, assuming 70% polarization. And in total, we had more than 8,000 points that were then analyzed as a pseudo data. And we achieved this result here for the impact on the transversity. So if we add electron proton data, then we get good constraint here in light blue on up quark, and for down quark, the constraint is not that great, but after adding helium-3 data, we have both up and down quarks that are very well determined for transversity, and the same happens for the fragmentation function Collins fragmentation function. And this is the result for delta U and delta D. Now I'm zooming into this pink blob corresponding to the extraction jump 20, and you see here results from lattice computation. Now, if we add electron proton data, then here's our result. It resolves well delta U, delta D constraints are not that great due to the predominance of U quark in EP results. But then we add helium-3 data, and this violet ellipsis shows the precision of the extraction that we expect after electron-ion collider data is available for those energies for proton and helium-3. And after we add helium-3 data, our precision of the extraction becomes comparable with a lattice QCD. We also realized that, of course, in order to accurately extract a tensor charge, one should have extraction in the largest possible region of X and Q square. And therefore, electron-ion collider, of course, gives a very, very large span on X and large span on Q square, but it leaves this corner here, which is typical for valence quarks open. And this corner here can be filled in by Jefferson Lab, and we used the solid projections from Jefferson Lab that would cover here the complementary region, this corner here towards larger values of X. In this plot here, you see the projected errors. Jefferson Lab will have higher luminosity, and therefore, on average, the errors are smaller for solid, but solid, of course, is not covering such a large region of X and Q squared. So we added both data from solid and electron-ion collider in our analysis, and compared to the base fit, which is jump 20, that shows here the percentage of error for up quark, down quark, up minus D quark transversity. And the impact for ASC is in blue here, solid is in green here, and together is in gold. So the lower, the better, the precision. So you can see that the large values of X for solid are important for D quark, for instance. The precision of extraction becomes better for D quark than for that of electron-ion collider, and together they give the best constraint for D quark. And solid also gives some additional precision in U minus D extraction. So we show the complementarity of electron-ion collider and solid results. So in my last slide, let me talk about accuracy versus predictions. We can have a very, very precise measurement. However, it cannot always guarantee very accurate extraction of the distribution. So here you can see the electron-ion collider ellipsis data projection, then solid projection in green, and then AIC plus solid in gold here. Notice that the center values change, and center values change because we have bias from the data which doesn't cover the whole region in X, and therefore, in order to have the most accurate extraction of tensor charge in this case, one should have the widest possible region of X and Q square covered. And we claim that the combination of AIC and solid covers the widest range, and therefore it would have the most accurate results. And together they would give precision which is better than the current lattice results. And this is also one reason to have interaction region 2 at AIC detector as well, in order to cover possible region. Complementarity is very important, and the coverage is very important. So this brings me to my conclusions. The tensor charge is arguably the least known of the fundamental charges of the nucleon, and it is unique because it sits at the intersection of 3D nuclear tomography, PSM, physics studies, and lattice QCD, including as much data as possible that is sensitive to the transversity, allows for the most precise extraction of the tensor charge that we achieved last year. And AC data on the Collins effect will allow for phonological extraction of the tensor charge to be as precise as current lattice calculations. And in order to reduce bias, of course, we need complementary measurements, and those from JLab and Solid in particular will provide this complementarity. Thank you.
Thank you, Alexei, for the very nice talk and also for staying in time.
As you see, it's all from Daniel. I just articulated it.
We appreciate you stepping in. There are a few questions. I see Aurore.
Yes, thank you, Alexei. Of course, Marco and myself are asking questions. So I have two questions. So the first question is about that there's a slide where you showed the precision for EIC plus solid. Can you go back to that slide? And there are those colorful curves. Yeah, this one. Okay.
Yes.
So about the D. So if you just take JAM 20, I see that there's a deep for D at high X. Where does it come from? Because there's no data there, if I remember.
No, indeed. I believe most probably it is the bias of the parameterization.
Okay. Interesting.
Yeah. And what's important, of course, is that the errors blow up, then we don't have the data. But otherwise, of course, these things can happen due to parameterization bias, for instance.
Oh yeah, because it blows up. But does it before it blows? You have a minimum, right? The question is, where does the minimum comes from?
Yeah, it's just. I think it's just from the this method. So if you look here, for instance, it's just because both of those functions they diminish, and therefore,
okay,
there is nothing.
Okay, and the second question is on that slide actually, and you really badly violate the software bound, like very badly. So what's your take on that? Because you seem to agree with Lattice, but it's a bad violation of software bound. So can you say something about your opinion about that? Sure.
Well, I wouldn't worry at this stage, actually, what the violation is happening. Indeed, we need data in order to understand whether this violation is significant or anything like that.
It is, because you don't need data to see that. You just have to plot a software bound on top of your plot, so you will see that you don't respect them at all.
That's right. We're actually exploring what happens if the software bound is taken into account. So, but at this stage, actually, this violation in this region there is some violation, yeah, but it's not that substantial. We studied that,
so you don't think there's a relation?
I don't think
result of the tensor charge and the software bound.
There's a big tension in this sense, yeah.
Okay, thank you.
Let's move on. We have 1 minute and there are 2 questions, Marco.
Wait, I'll try to be very quick.
Yeah, yes. Good morning, Alexei.
Morning.
This is Marco. I have a practical question. You have shown that the impact of the EIC pseudo data on transversity, but fitting basically all the pseudo data coming from all possible energy configurations. Yes. In reality, probably the EIC machine is not capable to run through all the possible energies. So did you try to explore the impact when you select a specific energy configuration? And if so, is there any one of them that is particularly suitable, useful to impact on the transversity and the tensor charge?
It's a very good question. We didn't explore that, and I think it would be very nice to explore actually.
Mm-hmm. Yeah, because this could be a useful info
of all measurements. We didn't try to compare one by one, but
yeah, this could be a useful input also in preparation for the detector, also
definitely
to know which energy is the best.
Okay, one last question, Bakur.
Hi, Alexei, thank you for the nice talk. I have a question. Well, it's actually maybe just a suggestion. You know, COMPASS is also going to collect some data. We will start in 2021. This year, deuteron transversity is the main, let's say, target for this data, for this run, which is transversely polarized deuteron CDS data. And I guess this will have quite some impact on transversity, as you know, D-quark transversity, and this will come way before EIC. I think maybe even before SOLID, if not in parallel. I don't really remember the timeline for SOLID.
Definitely, we're actually looking forward to it. So the main emphasis here was to electron-ion collider, but I guess for COMPASS, we'll just wait for the data, and I expect that we'll have better precision for this region here from the forthcoming COMPASS data. Yes, and I apologize for not mentioning this, but it will become more precise in future. Yes, also due to new data from COMPASS.
Absolutely. Thank you.
Thank you.
Thank you, everyone. If you have any more questions for Alexei, you can put them on the chat. Alexei, I will leave a question for you. But let's move on. The next talk is by Babu Pokhrel, who is going to talk about the transverse spin dependence azimuthal correlations of charged hadrons in transversely polarized proton-proton collisions at 200 GeV. All right, the floor is yours. You may start.
Okay, so you hear me and you see my slide, right?
Yes, very well.
Thank you. Good morning, everyone. I'm Babu Pokhrel from Temple University, presenting the recent preliminary results on transverse spin-dependent azimuthal correlations of charged hadrons in polarized proton-proton collisions at 200 GeV center of mass energy. So at leading twist, three-parton distribution functions describes the nucleon structures completely. The unpolarized, which is well constrained, it's shown in the top here. The helicity PDF, which is constant for quark, but poorly known so far for anti-quark and the gluons. The transversity, which is less known from the experiment, which I have highlighted here, and which we know from the previous talk as well, which is important piece of information for the transverse nucleon structure, and its extraction is difficult because of its chiral odd nature, which requires coupling to another chiral odd function, such as the fragmentation functions. And in PP collision, we can couple transversity to the fragmentation functions to extract the observable sensitive to the quark transversity. Actually, if we look at the detect the hadron pairs within jets in the final state, we can couple transversity with the Collins fragmentation functions here. And if we detect the hadron pair, oppositely charged hadron pair in the final state, we can couple transversity with the interference fragmentation functions. Here, the fragmentation function serves as a quark polarimeter. And this coupling leads to the azimuthal modulations, the azimuthal sinusoidal modulations, where this we call the single spin asymmetry, which is experimentally extractable and which provides sensitivity to the quark transversity coupled with the fragmentation function. In STAR, both beams are polarized, but we can achieve the single spin asymmetry by integrating over the other beam polarization. So for the extraction of the single spin asymmetry, we can use the cross ratio formalism, where AUT is the asymmetry and modulated by the azimuthal angle, sinusoidal modulation of the azimuthal angle phi weighted by the beam polarization. We can construct this by simply combination of the hadron yields or hadron pair yields in two detector half labeled as alpha and beta in azimuth. And by studying the different modulations, we can isolate different physics mechanisms, such as for the, if we detect the, for the hadrons within jets, the kinematics is shown in the left picture, bottom picture here. Phi s is the angle between the beam polarization vector to the scattering plane spanned by the beam momentum vector and the jet momentum vector, and phi h, which is the angle between the hadron plane is spanned by the hadron momentum vector and the jet momentum to the scattering plane. And the inclusive jet asymmetry, the phi s modulation of AUT probes the yields the sensitivity to the Sieverts effect, and phi s minus phi s modulation leads to leads to the sensitivity to the transversity coupled to the Collins fragmentation function, and phi s minus 2 phi h modulation yields sensitivity to the linearly polarized gluon coupled with Collins-like fragmentation function. And if we detect the hadron pair in the final state, the azimuthal angles are the pi s. Again, the beam polarization vector to the scattering plane is spanned by the beam momentum vector and the hadron resultant vector, which is sum of this pH1 and pH2 hadrons detected in the final state. And phi r is the angle between the scattering plane and the dihadron plane. And r is the relative momentum vector, which is simply the difference of pH1 and pH2. And phi s minus phi r modulation of the dihadron yields sensitivity to the transversity coupled with the interference fragmentation function. And in this approach, all the detector acceptance effect and the luminosity terms canceled out, which reduced systematic uncertainties. Moving on, the star has previously measured the pi plus pi minus asymmetries within jets, which is sensitive to the Collins fragmentation functions coupled with the transversity using 2011 data sets. Pi plus asymmetries are positive, pi minus asymmetries are negative as a function of pi on g, and the IFF asymmetries for pi plus and pi minus is a function of invariant mass using 2006 and 2011 data sets, where the significant asymmetry enhanced around the rho measured mass was observed. However, these results are encouraging. Statistical precision are limited due to the limited data sample size. Moving on, picture shows the star layout with different detector subsystems, the time projection chamber, which has coverage of -1 to 1 in pseudo-rapidity, and the whole 2 pi coverage in azimuth, which is used for particle tracking, momentum reconstruction, and for particle identification by measuring the ionization energy loss. The parallel electromagnetic calorimeter, which sits right next to the TPC, has similar coverage as TPC, and it provides event triggering by measuring the energy of the particle. The time of flight detector has also similar coverage as the TPC and acts as a stopwatch for its tracking an event, and works in conjunction with the vertex position detector, which helps improving the star capability, particle identification capability. And magnet is a solenoidal magnet which surrounds the whole configuration, which provides uniform magnetic field of 0.5 Tesla along G direction, which is used for particle momentum reconstruction based on the direction of curvature of particles inside the magnetic field. Showing the summary table where the 2006 and 2011 data sets are used for previous Collins and IFF analysis at 200 and 500 GeV, which are relatively smaller data sample. And the 2012 and 2015 data sets are used for the Collins and IFF analysis for which are based, these new results are based on these data sets. Actually, 2015 and 2012 are combined for the Collins analysis, which even makes the bigger sample, and only 2015 data sets is used for the IFF analysis. And the picture shows the kinematic coverage for Collins case and the IFF case, where star covers much higher Q square range, however similar to Compass and Hermes, which is rich kinematic for the transversity extraction. And the Collins and IFF analysis is performed in the mid-repeated region. I'm hereby presenting the preliminary results. The IFF asymmetries is a function of invariant mass for 5 PT beams. The PT increases from left to right and top to bottom in two pseudo-rapidity region relative to the beam direction, a polarized beam direction in forward and backward region, where we observe significant asymmetries enhanced around the rho measured mass, which evolves with the higher and higher PT. This is expected from the IFF model calculation. And the backward asymmetries are pretty small, although at higher PT, these are clearly non-zero. Next is asymmetry is a function of PT, again calculated in 5 different invariant mass bins. The average invariant mass average increase from left to right and top to bottom, again in 2 different eta bins, forward and backward. We observe pretty large asymmetries in forward region, which increase almost linearly with PT. Again, the backward asymmetries are small here. I forgot to mention that the systematic uncertainty here are pretty large because the major contribution is from particle identification, and we are working on this PID will be significantly reduced by estimating the 2 background size, which in this case we have estimated in a conservative approach. On the left, asymmetry is a function of integrated eta bins integrated over PT and invariant mass on the top panel, and the G, which is the fractional energy of quark carried by the hadron pair on the red points, and the blue points are the fractional momentum of proton carried by the quark, where the X increase almost linearly with the pseudo rapidity. So backward, we prove quark with the lower X, the forward, we prove quark with the higher X, and the similar effect can be seen in the asymmetries, where the backward asymmetries are small and forward asymmetries are pretty large as expected. However, the G almost is almost constant over the whole eta bins. The right panel shows the asymmetry as a function of invariant mass for the highest PT bin from the 5-panel result, and the bottom shows the corresponding X and the G, X on the left y-axis, G on the right y-axis, where X is almost constant over about 0.2. However, G increase almost linearly with the invariant mass bins. Here, the comparison between the 2000 star asymmetries with the theory prediction from Radici et al. I want to thank Radici et al. For this theory curve. So the 2015 results are much precise statistically, and so similar enhancement is the theory predicts here. Moving on to the next slide. Now I'm transitioning from the IFF results to the Collins, presenting Collins asymmetries as a function of particle jet PT. The left picture is the 2015 data from the 2015 data sets only, and the right picture is the combined 2012 and 2015 data, where we observe a significant pi plus, positive pi plus, and negative pi minus asymmetry, which are in favor with the theory prediction. However, the observed asymmetries are pretty large in forward jet scattering direction. However, the backward jet in the backward jet direction, the asymmetries are pretty small. Presenting asymmetry is a function of GT, which is the pion transverse momentum, relative to transverse to the jet axis. For different G-bins, the left picture is the 2015 data sets only. The right is, oops. Oh. Okay, I'm sorry. Okay, I think it's back again. So yeah, I was here. So so here the left picture again is from the 2015 only. The right is for the 2015 and 2012 combined for in forward jet scattering direction, where we can see the evolution of the asymmetries for different G-bins. The average G-bins increases from top to bottom here, and which are in favor with the theory. However, the observed asymmetries are pretty large relative to the in comparison to the theory prediction. However, in the backward jet direction, the asymmetries are almost consistent to 0 for all G-bins. Here, presenting asymmetry is a function of particle jet PT for kaon and kaon on the left and proton on the right. here we have observed the K on K plus asymmetries is about the size of pi plus asymmetries. However, within the statistical precision, but K minus asymmetries and the proton asymmetries are almost consistent to 0. And for backward jet scattering direction, the asymmetries are consistent to 0. Also, we have the Sievers and Collins-like asymmetry results, which are almost consistent to 0, which is on the back of slide. Oops. Okay, so I'm on the summary slide now. So we have measured the single spin asymmetry sensitive to the quark transversity. The IFF asymmetries are pretty large, with the prominent peak around the row measured mass consistent with the theory prediction. And the large systematic uncertainty in the IFF results, the major contribution from particle identification, which was estimated by the conservative approach in the signal region only, and that will be significantly reduced by preparing startless stuff, which mainly reduce the background, and by knowing the exact background size, the PID systematic uncertainty will be reduced significantly. And we observed the large pi plus and pi minus asymmetries in forward jet scattering direction, which is consistent with the previous measurement. Almost K plus is about the size of pi plus asymmetries. However, K minus and proton asymmetries are consistent with 0 within the statistical precision. And these new results are statistically precise relative to the previous measurements, and the IFF and Collins analysis using 2017 dataset at 510 GeV is ongoing, which is a pretty large data sample, and which provides broader, which covers much, which provides sensitivity to the different kinematic range. And the unpolarized dihadron cross-section measurement is in plan. And with this cross-section measurement results and the high precision asymmetry results will help to constrain transversity. Thank you for listening, and I'm happy to take questions now.
Thank you. Any questions? Marco.
Yes. Thank you very much for this presentation. And I have a question on the last item in your summary list. I'm really curious, interested to know your timescale for these unpolarized dihadron cross-section measurements, because probably you know that most of the uncertainties that come in my fit from including from the chi-square to the proton-proton collision data comes from basically the total ignorance we have on the gluon fragmentation into pions. And this can be constrained, of course, looking at the plus and minus data, but must be analyzed at the next unique order, and also from multiplicities in proton-proton collisions. So I mean, this measurement that you are planning about unpolarized cross-section is very, very welcome. So I would like to know when are you going to have it?
Thank you very much, Dr. Radici, for the comments. And I would say we are about to finalize these asymmetry measurements, and the next plan is to start. We haven't started yet, to be honest, and we will be starting after finalizing this. So I'm not sure how long it takes for this measurement, but we will be starting pretty soon.
Thank you.
Thank you, Babu. Are there any other questions? If any questions come up, you can use the chat to continue the discussions. Let's move on to the next speaker, Aurore Courtoy, who is going to talk about the constraint fit on the transversity through dihadron.
Okay, thank you. Do you see my slides?
Yes.
Wonderful. Let me just, okay. So thank you very much for accepting the talk. And it's a session about transversity and Twist-3 too, so that's going to be really interesting. So I'm going to talk about transversity through dihadron this time. So we heard about dihadron before, and I'm going to talk about different kind of fits, constrained fits actually. And it's a work that has been done with 2 students here listed on the slide. Okay. Oops. Okay, sorry. So we've heard about that already in the talk, but I'm going to just repeat just to make sure that we know what is transversity. So we have 3 leading twist pattern distribution functions, and the most known is the unpolarized that you see on the left, then the helicity PDF, and then the transversity PDF. And it's a PDF, so it can be also extracted from TMD point of view and then integrated. But to date, there are 2, well, one main approach to get the collinear one, which is the dihadron way. And that's the one you see on the right here. And I'm going to talk about this, the MEX 18, which is the Mexican transversity, and the pink one is the Pavia transversity. So to give you an idea, as you've seen, if you talk about dihadron and the coverage for the collinear PDF, you just take this this wonderful mapping of the kinematics here, and then you see that for the polarized PDF, you have a huge bunch of data. And then if you compare here, well, up to the talk we just saw before, that was last year we had this amount of data, which is not much. And actually, the blue ones come from cities, and the yellow one you see here come from PP data. So there's a huge reduced coverage that will be soon fixed. I understand it, and there are also the things that we need to take into account to fit PDFs. And actually, the transversity PDF is that we have to respect a few things, like first principle constraint, especially positivity for all PDFs, which reflects here for the transversity as a software bound. So that's the continuation of the positivity constraints on all the other PDFs, which is the sum of half the sum of the unpolarized and the helicity that must constrain the transversity PDF. And also, if you take, that's mainly a large X. And then a small x, we basically have integrability. So we have to integrate to be able to integrate the transversity to get a finite tensor charge, which seems pretty convenient. And so that's basically what I was just saying. And there are few constraints based on first principle for transversity. The thing is that we don't have any constraining sum rule if you compare with the other PDFs. It's actually the other way around. We need the sum rule, which is not really a sum rule because it changes in Q. So the first Mellin moment gives a tensor charge. So that's what we want to get. Instead of constraining from this Mellin moment, we actually get a number for this Mellin moment. So that's an output of the, instead of being an input to the fit. And so there are a few things you need to do about the transversity is that you have to impose the positivity bound, the software bound, that's the one I just mentioned before. And you have some behaviors like the endpoint behavior, like you want to go to 0 when x goes to 1, and you have to have the support property too. And the main difficulty with this transversity PDF is that it's the chiral lot object. So you need to pair it with something else. So you can't just take inclusive DIS. You need to pair it in semi-inclusive or in PP or E plus E minus. PP and then all those things. And so here you have the data for E plus E minus that are the one that constrain the partner, the fragmentation function partner that you see here. And then the CDs and PP data and other data give you the transversity here. And that's basically what we have. So you need to have like 2 objects at least to get a transversity. That's the main difficulty we have for this object. So once you have the data, what do you do with the fit? So you have the data, which is already a huge thing. Then you need to take into account the first principles, and those ones, they are untouchable. Let's say here they're not assumptions. Then you can make extra assumptions. And here there's a quotation mark here that though they are untouchable, sometimes the way you implement them depends on data-based extractions. For example, if you want to impose the positivity bounds in this case, it relies on the positivity for G1 and H1. Oh, sorry, F1. That would be F1 and G1. Okay, sorry. So basically, the way we will impose a software bound here depends on the extractions of the previous PDFs, on the unpolarized and the helicity. But still, the first principle in itself is untouchable. We have to respect it as much as we can. And then there's a theoretical framework that we've seen there are different, that we heard about this TMD, and then the collinear twist-3 analysis. And then here, there's the collinear dihadron framework. And then there are some assumptions, QCD based or not. There are parameterizations, and then there's this error treatment, which eventually should reconcile all those points together in a beautiful way. And the way we do all those things just gives the signature of a fit. So that's basically, that's the recipe for one fit or another. Okay. So the first try to extract the transversity, well, here I quoted the Pavia group, but there were fits before by the Torino group, impose the positivity bound from the parameterization. So you can see it here. That's what I think they see it in Pavia. So you have this transversity here, xh1, and then you multiply by a function, and then you divide by the norm of this function, and then you multiply by the software bound. And then you have the flexibility coming from this function f, and then you impose in an implicit way these conditions. And you can very good fits. I think it's really, really good. But what you see here, what you saw at that time was a clear saturation of the bound. Now, if I understand from the Pavia 18, where they have the PP data on top of that, so it's a global fit, they show that there's a slight release of this saturation from the bound. But then there was some questions, some things to think about. So so the first thing we realized 6 years ago already is that maybe there was room for improvement, because we checked the deuterium data. Here you see those blue dots. They seem to have to be in tension with the software bound. That's what we call tension, because we don't really know if it's what tension means, but something that is not agreeing with what we see from the software bound. And then came this discrepancy with the lattice evaluation that I took this plot from Marco. And then you can see that lattice finds GT around 1, and all the other extractions except JAM, that in that case took into account the lattice data, find something that is smaller. So is there room for improvement here? That's a good question. And as it was mentioned before, actually GT is pretty important for BSM. So that's a good thing to think about. And instead of room for improvement, I think there's opportunity for improvement. And what we have seen is there have been these two papers thinking about the impact of the software bound, or the way we implement the software bound. So that's the work I'm talking about here, this one with Benel, which is our work. And there's another one by, I think Carlo is there connecting, right? D'Alessio Procudin and Carlo Flore and collaborators thinking about this software bound. And then also there was the talk we just saw by Alexei that just said, okay, if we rely on the software bound, it seems we can find actually a good agreement with the lattice. So to that point, there seemed to be no reconciliation between the positivity and the lattice. So we have to think about it. So the other thing that we can do, that's what we've done in this paper I just mentioned, is instead of imposing the positivity by the functional form, we put it in by the fitting procedure. So we just impose it through the fitting procedure. And we do it with 3 different steps. So the first step would be to understand what is kind of not wrong. What is the tension? How tense is it, right? So what is the difference between those data and the software bound? So here I just showed a plot here for the deuterium data from COMPASS. And then you see that here there's what I call a weight that is, I think, defined here, this weight here. And I weight this compatibility between the software bound and the data. And then you can see here that is not a really good agreement here with the error. And then here too, this point here is totally like not in favor of the software bound, and those two have a really bad weight too. So the first thing we do is that we weight the chi-square in the fit with those tensions between the data. Well, this is not, there will be not the data, that is extraction from the data. So that's the point by point extraction and the software bound. So this relies, as Marco just said before, it relies on the DIFF too, right? So the better we know the DIFF, the better we would do this analysis too, right? That's really important. The second thing we do is that we try to, of course, parameterize the x dependence, and then we try to span as much as we can a small x. And the large x, we know it has to fall off because we don't want to implement here the software bound. So we need to make up for this y minus x to some power that we had from the software bound. And then what we do here, we just try to take a functional form that goes, that mimics this fall off. And then at small x, we fix a value of x that is based on on small x analysis, and then we just modulate the rest by those Burson polynomials here. So that's the basis we see here. So we have four different functional forms here. That's what we do. And then the last step is, since we did not really impose software bound, and by the way, this software bound I show here, it's not exactly correct. There was an old plot just to see how things work, right? Since the software bound was not imposed, we still had to make sure that we don't go crazy out of the software bound with this functional form. And as you can see here, sometimes, so just check. So the first minimization will be the red one, this one here. So for the up, it will be this one here. And for the down, it goes here. So as you see, if we don't impose, so with this functional form, we can find something that is pretty decent, but still it goes really low for our point of view, because it would be really outside of the software bound. So what we can do too is, and that's just one example, there are others, of course, is that we impose constraints. We impose with the Lagrange multipliers. So we just, in 2 different points, we impose that this the second iteration of the minimization should be inside the software bound into 2 different points. So we just take 2 values, 2 different points. And actually not on the software bound, but just points we decided that were important for us. And as you can see, then it goes inside with this Lagrange multipliers. So then we make sure that we make an envelope that is close to the say software bound. And that's how we do. And that's what you find here on the left. That would be for the up. So I just quote here the 68% and 95% confidence level here. And that's for the down. And as you can see, where we have data here, we have a narrow band. And when we don't have data, we have a bigger band here. And actually here, we allowed the down to be a bit outside the software bound, because that's where we have more tensions. That was a desired effect, actually. And if you compare with the Pavia group, you can see where we have data, we kind of agree. And when we don't have data, we have a difference in the error treatment. Okay, and so we see that there's more flexibility at large X, first here for the down, and also that the chosen functional form allows for a wider uncertainty at both small and large X. So that's what we wanted. We wanted to reflect the lack of data here and here. The same for the up, but we don't see it that much. And so that's what we think it's a balance interplay between the constraints and the data. So that's what we get. So now if you want to compare with lattice, so that was a plot we've seen before. I just added our point here. And as you can see, the up seems to be the most constrained, kind of, and the up is the less constrained from the IFF, at least. That's what we see. And if you check GT, we're here, and we kind of we can agree with lattice. So this exercise was made to actually show that you can get an agreement with the lattice if you get a more flexible functional form. And also, I think the error play a big role in that. Of course, you can see we have a huge error. And this huge error is not because, okay, thank you, Martha. It's not because of this, of just the fact that we want to be conservative. It reflects the lack of data. And also, I'm sorry. Okay, so that's the plot we just saw by Alexei before. So I just overlap it with software bound. So that's not the same scale, but then you see the software bound here. So up is kind of okay. So it goes a bit wide here, but down is totally outside of the software bound. So it seems that we have to understand something here, because it seems we cannot, up to now, reconcile this positivity and lattice. So something has to be understood here. Okay, and talking about this comparison with lattice, I just show here, so that's our result for GT. And I wanted to show, so that's the average we have here. The stack histogram. So for each functional form we had, remember they were color. So I show here the functional forms that we have defined, and that would be the value we have for GT. So it's stacked. So you just have to you just sum them, right? So you see the green here as a huge error band at small x, and you see how it spans GT, which means that it actually matters for GT. While if you have a really narrow error here, for some, that's the pinkish one, then you find something that is narrow for GT2. So of course, small x will be really important for this tensor charge, for its error and central value as well. But I mean, the error is much more important, I think, right now. And of course, the IC will be really helpful for that. Okay, so I go to my conclusions. So I just show you the constraint bit about the transversity, and it reflects the tension with the software bound through a statistical reweighting of the data. That's what we've done. And the way we constrain it at large X is through the functional form and the Lagrange multipliers. We still have to understand a few other things. And of course, it's not a global fit because we don't include the PP data. But what we show is that this treatment of uncertainty showed that there could be a compatibility for both positivity and lattice results. So I think we have to explore that a bit more. That's the students involved. And just an announcement, quick announcement. We're going to have Hadron 2021. It was supposed to be somewhere on the beach, but it's not happening. So it's going to be online. And it will be a huge, it will be an exciting session about QCD and Hadron structures. So that these are the conveners. So please register if you're interested. Thank you.
Thank you, Aurore. Are there any questions? Let me ask Bakur.
Yeah, thank you, Aurore, for this nice talk.
Thank you.
Again, we are going to have Deuteron data, so we will provide more information about Dihadron columns, right, for your fits. But I just wanted to comment about the data points. Looking at the, I don't know which slide it is, slide 12 probably.
Wait, let me go.
The main.
Here. Those ones? That's not with the data. So I don't think I plot with the data here.
I have a different slide. I downloaded your slides and slide number 12 is something else.
Okay. I'm not sure I had a plot with the data. I'm sorry.
Two slides forward, if you.
Oh, this one here. Sorry, this one.
2 slides forward, where you have the first fit, the first minimization, and then the second.
Okay, sorry. Yes.
Yeah, I guess here looking at the points, they are not really in tension with the software bound, because within uncertainties they're kind of okay. I guess the main tension comes with when you introduce your function. So when the function, you want the points to follow certain fitting functions, certain functional shape, and then this comes into tension with the software bound. At least this is what I see with your first minimization curve.
Right.
So then I'm not sure reweighting the points is really a good approach here, because probably one has to rethink the fitting or the functional form or the I don't know.
Okay, so maybe the word reweighting was not.
Please.
Yeah. Okay, so what I mean by reweighting is basically it reflects. Okay, maybe you can see it here. Okay, it's just here. So what it will change? It will change just the size of the error band. So I don't shift the data. I just change the size of the error band.
Yeah.
Okay. With this tension. And of course, so what we did here, what the idea we had is actually we don't impose a software bound at all. We just guide here, because if I let it free, of course, this guy can just blow up, right? So what we do is just impose a few points, and then we have more flexibility. And as you can see, as a result of that, we actually don't constrain this one here. That was just one example, but of course we have other curves that go through this data, right? So you see the result here. That's those guys will be really happy here, right? So we don't do that. So that was the idea. Instead of sticking to this software bound here, we remove this red curve, and that was the contribution of this paper, that we don't impose this, and we think this fitting procedure with a different functional form to allow those points to be included in the fit, to be actually covered by the fit, right?
I see. Okay.
So the tension is here, but it is not a huge tension. It's not 5 sigma. Yes, I agree with you. Yes.
Yeah, tension sounds really, for experimentalists, is something way more serious. Here they are just compatible. Okay.
Right. No, in that case they are not. Yes, it is not incompatible. But if you want to include those ones properly without saturating the bound, you really need to be more flexible from a functional form. Yes.
Yeah. Okay.
Thank you.
Okay, if there are more questions, we can continue this on the chat. Let's move on. Our next speaker is Raj Kishore, who is going to talk about a new method to extract the valence transversity distributions. Raj, are you able to share your screen? Can you hear me?
Yeah, I can hear you, Marco.
Okay. Raj?
Looks like he's muted.
I did see Raj in the participant
Your time
list.
for talk is there. Where are you? Yeah, please unmute yourself. Okay.
Am I audible?
Raj is there. I'm talking to you over the
Hello?
phone. Okay.
Hello, I'm audible.
Yeah, now you are audible, I guess.
Yeah, sorry.
Yep.
Sorry for inconvenience. Yeah, so
Can you share your screen, or you have
Yeah.
trouble and I need to pull it up?
yeah, just wait. I will just share my screen. Okay. Perhaps I'm not able to see how. Sorry. Oh, yeah. Sorry. Yeah. Is my slides visible now?
Yep, you can start.
Yeah, sorry. So, sorry for inconvenience. Myself, Raj Kishore, I'm going to talk about the new method to extract the valence transversity distribution. And this work has been done in collaboration with Azimuthal Mukherjee and Morales and Mino. And you can find the details in this reference over here. Okay, sorry, let me put in the full. Okay, so. So my plan of the talk, I will first, briefly talk about the transversity distribution, and then come to the formalism where we studied this weighted single spin asymmetry, and then come to the suggested probe to the transversity distribution using the difference asymmetry, and then we will talk about a new probe to transversity distribution, and then after we will give the numerical estimates for that. So starting with that, although this has already been discussed in the previous talks, I just briefly go through it. The transversity distribution is a fundamental and necessary information apart from the unpolarized distribution functions and the helicity distribution in order to fully understand the quark structure of the polarized hadron in the collinear configuration. So the transversity distribution is defined in this expression over here. This one. But this transversity distribution is a chiral odd function, and because of that, it decoupled and cannot occur alone in the deep inelastic scattering process. So in order to prove this transversity distribution, it just has to couple with another chiral odd functions, which can either in the initial state or in the final state. So Alcin-Mino group and in this reference, they studied the double transverse asymmetry in the transversely polarized proton-antiproton scattering process in order to prove this H1. So this H1 can also be studied in the series process, as we have already seen in the previous slide talks. And by here, I'm just showing here, by studying the weighted single spin symmetry, we can prove this H1. And here the H1 is coupled with the Collins fragmentation function. So coming to the formalism that we took here, we considered the series process where the only one hadron is observed in the final states, where this unpolarized lepton spins collide with the transversely polarized target proton, and the cross section is given in this expression over here, where the ST represents the polarization of the target proton, and here the contributions we took only which are relevant to the Collins asymmetry, and the others contributions are also there, but with the different weight functions. So this FUU and FUT are the structure functions, and in the Gaussian parameterization, it can be given in this expression over here, where the unpolarized phase, this FUU have this expression in the convolution of the unpolarized PDFs with the unpolarized fragmentation functions, where for the transversely polarized target beam this FUT have this expression, which is in the convolution of the transversity distribution and the Collins function. Okay, so we here study the single spin asymmetry, which is a particular here in the series process, and it is defined as this weighted azimuthal moment, which is given in this expression over here. So this in the numerator, this difference of the cross section, polarized cross section, is giving these expressions, which is having this, which is the part of containing the convolution of the H1 and the transversity distribution and the Collins fragmentation functions, where this in the denominator, the sum of the unpolarized cross section, basically it's sum of the transversely polarized cross section, which is giving the unpolarized cross section, is giving this expression over here. So when we study this this weight function, when we considering this weight function sin phi h upon plus phi h, the contribution to the single spin asymmetry is coming from the Collins functions, which is given in this expression over here. So in this reference here, in this reference, they studied this. They suggested a probe to the H1, this H1 in the series process itself, and they given this cross section in the notation form, where this plus minus represents the observed pi plus pi minus in the final states, and the T represents the target, that is here the proton and the neutron here. So comparing with this, the previously written the cross section for the series process, the sigma 0 is having this expression over here, and the sigma c is having this expression, which is having this expression, where AT and this BT B of BT represents the transverse momentum dependent part here. So the measure of the Collins asymmetry is basically this ratio sigma c over the sigma 0, which is having this expression, and which is basically 1 by TNN factor of the usually measured asymmetry in the experiment. So if we measure this pi plus pi minus in the final as a final hadron, and then the sigma 0 and the sigma c can be given in terms of the PDFs, flavored and disflavored fragmentations, and the Collins functions, and in terms of the transversity distribution as well. So for the proton as a target, the sigma 0 and the sigma c and the sigma 0 is having this expression, and for the deuteron as the target, we have expressions, this expression for the sigma c and the sigma 0. So, but the PDFs are defined in these two rows, first two rows here, whereas the unpolarized fragmentation, this favored and disfavored unpolarized fragmentation functions is given in this the third and the fourth row over here, whereas the disfavored and the favored Collins fragmentation functions is given defined in these two last two, that is this fifth and the sixth column row here. Okay, so now in this reference they use the difference asymmetry in order to probe the H1. So which is defined here. The difference asymmetry is defined in this expression over here for the positively and negatively charged hadrons. Here they have considered the pions. So for the proton target, this difference asymmetry have this expression over here, and for the neutron target, we have this expression for the difference asymmetry. Though we can see in both the expressions we have this Collins functions dependence over here, which is both same in both the expression. So if we take the ratio of this difference asymmetry, it cancels out the Collins fragmentation functions dependence, and it just have the dependence of the PDFs and the fragmentation functions and the transversity distribution, which we can see in this expression over here. So okay, so this difference asymmetry can also be extracted from the measured Collins asymmetry data and from the unpolarized cross section as well, which is through this expression over here. Now, so in this reference, they extracted this difference asymmetry from the compass data on this, the Collins asymmetry with the statistical uncertainty, and they show the difference asymmetry in this plot, where the red defines for the neutron target, proton target, and the black defines for the neutron target over here. And from this data, they extracted this ratio, the ratio for the difference asymmetry for the deuteron and for over the by the proton target over here. And using this data and using the expression for the difference asymmetry in the previous slides, they extracted the ratio of the down quark and the up quark transversity distributions, knowing the fact that by assuming once knows these unpolarized PDFs and the fragmentation functions. So from these plots, we see that these difference asymmetries are the small quantities with relatively large errors, and it's mainly because it is related to the ratio sigma c upon sigma 0, which is proportional to this particular factor over here. We will see that in the numerical estimates again by after giving the parameterization to this one. And the ratio, if we take the ratio of these difference asymmetries, although the difference asymmetries are the smaller quantity and having the relatively large errors, this is the ratio is bound to have the huge uncertainty, which can be seen in these plots over here. Okay, now those shortcomings that can be limitations can be overcome in this when we define this ratio over here, this RC, which is basically the ratio of the difference of the weighted polarized cross sections in this, and it is motivated from the measurement of the sin phi h plus phi s modulations of the SIDS cross section, and which is basically related to the sigma c over here, and if we measure for the different targets and for the observables for in the final state is pi plus and pi minus, then we can construct this ratio. And in this expression, we see that this ratio has a very simple Pitonyak interpretations where we don't see any dependence on the Collins functions as well as the unpolarized PDFs and the fragmentation functions as well. So unlike this difference asymmetry which we saw in the previous slide, this ratio doesn't have is not the ratio of the two small quantities, rather because the numerator and the denominator are simply the proportional to this very factor, this one. Okay, so in order to give the numerical estimates to that, we use these parameterizations from this reference over here, and this is for the Collins asymmetry, which is parameter in terms of the unpolarized fragmentation function here. This is the Collins fragmentation function, which is parameter in terms of the unpolarized fragmentation functions, and this NQ is given in this expression over here, which alpha, beta, and this NQ is the free parameters. And similarly, for the transversity distribution, we have this expression over here, where this is the unpolarized PDFs, and this is for the helicity. This is helicity distribution, and this again is given in this expression over here, which is where NQ and rho and sigma are the free parameters, and these free parameters. Sorry. Hello.
Continue.
Yeah. Sorry. So okay. So these free parameters has been extracted for the up quarks and the down quarks from the Hermes compass and the Bell data in this reference over here. So we use this MSTW PDFs, and the pions fragmentation functions are taken from this reference, and the helicity distribution are taken from this reference over here. So using those parameterizations, we plotted for the difference asymmetries for the deuteron target and for the proton target. So deuteron target in this plot and for the proton target in this plot with respect to X. So at the fixed QA square value, which is 2.41 ZBA square, and the PT is integrated over 0 to 5 ZeV, where the Z is integrated for 0.1 to 1 ZeV. Sorry. And in the lower two plots, we saw the numerator and the denominator of the new proposed ratio, that is RC, with respect to X as well here. And here again, it is at the fixed QA square value, that is 2.41 ZVA square. here. This is for the numerator and this is for the denominator. And here the PT dependence part cancel out in the ratio, whereas the Z is integrated over 0.1 to 1 as in the previous these two plots. Okay, so from these plots we can clearly see that the numerator and denominator are is relatively larger as compared to the this difference symmetries. So this overcomes this. We cannot see. I mean, like we can have relatively lower uncertainty by measuring this numerator and the denominator. So here come to the conclusion. We saw a probe to the transversity distribution using the concept of the difference asymmetry for the different targets, proton and neutron here, and for the positive and negative hadrons in the final states. So this difference asymmetry we saw, it's a small quantity and having a relatively larger error. So taking this ratio will cancel out the, although it's cancel out the Collins functions dependence, but it is bound to have the large uncertainty. But the ratio RC, although it can be estimated from this modulation of the sine phi plus phi modulation of the transversely polarized CT's cross section, and we have simple interpretation for RC, which can directly probe this H1 dV upon H1 UV, which is basically the transversity distribution of the valence down Gauge upon transversity distribution, the valence of both. And from this, we are confident that the simplicity of this ratio RC and in terms of the transversity distribution will prompt and encourage their measurement. And this could be done, measured during the next neutron compass run or during the ongoing Jefferson lab experiment or on the, or can be measured at the future electron and collider. Thank you for your attention.
Thank you. Are there any questions for Raj? I don't see any raised hands, but let me ask you, do you have plans to extract moments using your method?
I guess we are planning to extract this ratio from ratio of the transversity distribution, because this race, when we are taking this ratio, it's giving the simple Pitonyak interpretation in terms of this ratio of the transversity distribution.
One question from Gunnar.
Yeah.
Hi. I was wondering, in the approach of the difference asymmetries, you rely on the cancellation of the fragmentation functions, and for that to happen, you need to have factorization, factorized ansatz for the distribution in the fragmentation functions. Now, for the TMD asymmetries, you usually involve a convolution over transverse momentum in the expressions. So for the unweighted asymmetries, you don't have a simple factorized expression. How do you deal with that? It actually, especially if the transverse momentum dependence of the fragmentation function and PDFs are different for the different flavors.
Okay, so although this expression for this cross section, we have this cross expression over here. So when we taking when we are measuring this difference, it is having this expression, and it is in terms of they are already seems like it's factorized one in terms of these functions and this transversity distribution over here. So like when we are integrating over the z, so since this depends upon the x value only, and we are integrating over the z, so this will cancel out when we are taking the ratio over here.
But your A and B's, which you have there, which you write there as a function of PT, they are in general not just a function of A and of PT. They are also functions, first of all, flavor and also of X and Z. or can be.
Okay, so based on this parameterization over here, so okay, so previously we saw this parameterization here. The PT dependence are like separate out from these convolutions that this are transversity and the Collins fragmentation function. So I guess this will cancel out in the ratio. This dependence on the PT when we are integrating the PT. Yeah,
but only if you don't have any flavor dependence here, and also no kinematic dependence, which in general you don't actually assume that it's completely independent of kinematics. In fact, there must be some kinematic dependence. So I do not know how much the approach actually brings us. Probably it's worthwhile trying out putting in some of the different parameterizations for the PT dependence, which are on the market right now, and see how much does this influence your extraction in accuracy versus other extractions, for instance. Then yes, because that will always be a simplification of the approach and an approximation, which will come with a systematic uncertainty that needs to be quantified at some point.
Yeah. So I mean, these parameterizations of the PT, basically the factorizations of the PT is taken from this reference over here, where they have considered the kinematics in the, I mean, lower QA squared, sorry, this in the lower QA squared region. Yeah.
I think we can take it to the chat and then
yes, please. Because we have the next session starts at 10. We are running very late already. So please continue this discussion in the chat. And thank you, Raj, for your talk.
Thank you.
Let's move on to the next talk. We switch gears a bit. We will talk about Twist-3 PDFs. Shohini Bhattacharya is going to talk about the zero modes and the matching for the Twist-3 PDFs. Shohini, you may start.
Okay. Can you see my screen?
Yes.
Okay. So good morning and good afternoon, everyone. My name is Shohini, and I'm going to talk about zero modes and matching for Twist-3 PDFs. We'll see very soon what these jargons imply. This work has been done with the members of Extended Twisted Mass Collaboration. All right, so PDFs can be classified according to their twist. What that means is that if you calculate a physical observable, then Twist-3 PDFs appear suppressed in parts of the hard scale for the process. There are 3 Twist-3 PDFs, E, GT, and HL, but unlike Twist-2 PDFs, Twist-3 PDFs do not have such a density interpretation, but they can be related to quark-gluon-quark correlations, and as such, certain x-square moments of those functions are related to the average force experienced by quarks in DIS. Because of this kinematical suppression, they are incredibly difficult to extract from experiments. Therefore, it would be great if we could extract them from lattice QCD. But the problem is that light cone PDFs come from matrix elements that have time dependence, and as such, they cannot be directly computed on Euclidean lattices. In 2013, there was a breakthrough proposal by G to calculate instead quasi-parton distributions. So this method relies on the extraction of matrix elements for boosted nucleons involving quark fields separated along spatial Z3 directions. So because of the spatial nature, they can be directly computed on Euclidean lattices. So quasi-PDF approach has now made it possible to directly extract the PDFs from lattice QCD. Now, before getting into Twist-3 PDFs, let's quickly go over a calculation for F1 with a spatial correlator and the Dirac structure gamma 3 in the infinite momentum frame. So let's imagine that you want to calculate the contribution of this ladder diagram to F1 You start with an expression like this. Just follow me. Let's not go into nuts and bolts of this equation. So P3 over here is the Z component of the target nucleon. Now, a standard way of dealing with these loop integrals is to decompose K in terms of the normal coordinates. The K0 integral can be done using contour technique. And if you take the large momentum limit prior to performing this K-perp integral, you exactly get back your light cone result. So this is the UV pole, and that is the infrared singularity. Unfortunately, this limit cannot be taken on lattices. So what if I now repeat the very same calculation, keeping P3 finite, but at the end of this step, for large P3, I do a systematic expansion in inverse powers of P3. So essentially, let's just reverse these two limits. In doing so, we get a result like this. So let's now go through some important features of such a result. We see that we get a non-trivial X dependence in these unphysical regions. However, we get an infrared singularity in only the physical region. And very importantly, this is the same infrared divergence that you get in your light cone result. Very interestingly, quasi-PDF results are UV finite, but they appear back once you integrate over X. So the takeaway message is that these two limits, that is whether you take the large momentum limit before or after the K-perp integral, does actually matter. And the non-commutativity of these two limits leads to two things. They lead to non-trivial differences in the ultraviolet behavior of these two distributions. However, the infrared poles are exactly the same. So because of this, quasi and light cone PDFs can be matched, or they can be related through a perturbatively calculable matching coefficient. At one loop, you can show that this coefficient is given by the difference between quasi and light cone corrections calculated in quark target model. So we tested this factorization at one loop order for the first time at Twist-3. We work in the Feynman gauge, for which these are the real diagrams, those are the virtual diagrams. For the ultraviolet divergences, we work with DIMREG, dimensional regularization, and for infrared, we work with non-zero parton masses as well as dimensional regularization. Now I'm just going to focus on this ladder diagram because it's just this diagram that gives rise to new features at Twist-3 relative to Twist-2. Let's get started with light cone GT, which is defined in terms of the Dirac structure gamma I, gamma 5. These are the target attributes, and in particular, this is the target mass. But the target is the quark itself, so we essentially have the quark mass. So based on this, you see that you cannot set this quark mass term equal to 0, but rather you would have to extract linear terms in MQ from that side and then set MQ equal to 0, provided you are not using it as an infrared regulator. A simple trace algebra will give rise to 1 power of K minus in the numerator, and a corresponding calculation of the numerator for Twist-2 PDFs will be independent of K minus. Now this is very interesting because it gives rise to two interesting features at Twist-3. So experts have shown that in quark target model calculations, they give rise to discontinuities in Twist-3 GPDs at the crossover points separating the Glab anormal region. But even more interesting, these discontinuities pile up to become a representation of delta function in the forward case. And these are the zero modes that we often hear of. And this talk is about the non-trivialities that we encounter in matching because of these contributions. So you can disentangle your ladder diagram result into a singular term and a canonical term, and this has the delta function term. This is how your light cone GT looks like prior to carrying out these K-perp integrals. Now this is going to have both UV and infrared divergences. So let's just work with quark mass first and see what comes out. what happens is that the ultraviolet pole cancels the epsilon UV present in the prefactor such that a delta function, this one over here, survives in your light cone GT. However, if you work with dim reg for the infrared, you see that the DR regulated infrared pole also allows for a delta function, but with an opposite sign, and therefore the delta function drops out in your light cone GT. So for the first time, you see that the appearance of the zero modes is actually an infrared scheme dependent feature. The calculation of the canonical part is much simpler, and these are the three different results that we get in three schemes. Note that the structure of these infrared poles look exactly the same in all three cases. Now quasi-GT. Quasi-GT is defined in terms of a spatial correlation function with the same Dirac structure gamma I, gamma 5. You can disentangle once again your ladder diagram result into a singular and a canonical term, and I'm just going to focus on this singular term for the next few slides. So for these singular terms, after a K0 integral, we get a functional form in K perp, which for non-zero quark mass is both UV and infrared finite. So your overall result is then proportional to epsilon, and therefore the singular part drops out from the discussion. But now if you set the quark mass equal to 0 right from the start, then for the UV part of this K perp integral, once again, you're fine. However, you run into an infrared divergence at the point x is equal to 0 when K perp goes to 0. So what we did is to isolate a region around x is equal to 0, switched on dim reg, and we get a result which is proportional to 1 divided by modulus of x, whose power is a bit deformed from 1. This is a non-trivial term to expand in terms of epsilon IR. Nonetheless, we showed that in the sense of a distribution, you can extract the expected infrared pole that I just discussed at the point x is equal to 0, plus you get some other finite terms. So this pole cancels the epsilon present in the prefactor such that a delta function now shows up in your quasi-GT. So once again, we see that the appearance of the zero modes is an infrared scheme dependent feature. These are the results for the canonical part of quasi-GT in 3 schemes. And note that we get infrared poles in only the physical region, and the structure of these poles are exactly the same in all cases. Now, obviously, if you want to have matching, as I said, you should check if there is an agreement of the poles between light cone and quasi-PDFs. As far as the singular terms are concerned, our result is infrared finite, so nothing to worry about. But for the canonical terms, take a look at your quark mass case first. This is the light cone result, that's the quasi-PDF result. If you just focus on the poles, then you see that they exactly agree. Same story for gluon mass, and the very same story for dim reg. So the infrared singularities exactly agree for all 3 regulators, and diagram by diagram, we find that all the poles agree, which is at the very core of this quasi-PDF approach, as I stressed right at the beginning. So this is the matching coefficient for GT in MS bar. It's remarkable that at the end of the day, when you calculate this coefficient, it's independent of the infrared scheme. Now, what is done in practice is to embed this coefficient into a matching formula, which then involves the convolution of that with the non-perturbative input for quasi-PDF from lattice. I'm going to blur this delta function since it doesn't contribute to the convolution. However, there are major issues with this part of the equation. So let's go through that. The real corrections for quasi-GT scale as 3 divided by 2 xi for large xi. So because of that, after a convolution, when you calculate the norm for the matched PDF, you hit a logarithmic divergence. This is the same UV divergence that you miss in your real diagram results, as I explained before, but they kind of hit you back when you calculate the norm for the matched PDF. So because of such divergences, the norm for matched PDF does not agree with that of quasi-PDF. This needs to be fixed. So what we do is to use a modified MS-bar scheme, whereby we subtract these divergences from outside the physical region and we impose a norm preservation. So that means that we also subtract some finite terms. The end product is a matching coefficient in a full plus function format, which was then implemented by the ETMC collaboration, and I refer to Krzysztof's talk for our results for the X dependence of GT. Finally, let me talk about ENHL. So your light cone HL always has a delta function, no matter which infrared regulator you work with. However, they always come in with prefactors that depend on the infrared regulator. And this is a problem because if you take a look at your quasi-HL, it looks like that. So at first glance, it seems like there is a disagreement in the infrared pole structures of these two distributions. So what's going on? So let me just give you one example in the context of working with quark mass. This is your quasi-HL proportional to 1 divided by square root of x squared plus eta square, where eta is the ratio of MQ divided by P3. If you take the large momentum limit or you do a twist expansion, you get a structure like this, which no way looks like a delta function times the singularity. So doing a twist expansion before you calculate the matching coefficient tells you that you cannot calculate the matching. But you have to keep in mind that in matching formulas, we have integrals. So we treated our quasi-PDF results in the form of a distribution and showed that you can rewrite your result such that you exactly recreate the effect of the delta function with the singularity to a leading order in the expansion of infrared regulator, and hence everything is fine. So the point x is equal to 0 is pretty delicate for quasi-PDFs. I won't go through the details, but this is the matching coefficient for HL in modified MS-bar scheme. This result is independent of the infrared scheme. And I once again refer to Krzysztof's talk for our first results from lattice QCD for HL. So I don't know how much time I have, but very quickly, we extracted the matching coefficient for the Twist-3 PDFs for the very first time. The presence of singular zero modes makes the extraction pretty much non-trivial, but nonetheless, we laid the necessary theoretical principles to deal with the complications. And right now we are looking into Twist-3 matching results by Brown and co-workers. Thank you very much.
Thank you, Shohini, for this nice and clear talk. In the interest of time, please formulate your questions briefly so we have some time for the speaker to answer. Alexei?
Hello. So I have actually many comments and questions, but I will just make a statement. So if you look inside of our paper where we computed something similar, but we actually made a full computation, including this free part. So my comment is that actually, if you look only at GT contribution, which you explore here, you'll find out that our expressions are different. Because the GT contribution which you consider comes not only from 2-point diagrams, but it also have some contributions from 3-point diagrams, which you ignored. So that's probably my main comment.
Yes, that's correct. In our very first shot, we wanted to stick with the machinery for Twist-2, but like you're saying, if we consider the quark gluon quark correlations, then it, like you show in your paper, the matching coefficients for the Twist-2 and the Twist-3 parts for GT are different. That's correct.
Exactly. Thank you.
Alessandro?
Yes, can you hear me?
Yes.
Okay, so first of all, Shohini, thank you for the nice talk. I have a general question. Usually there are relations at the integral level between G1 and GT, like Burkhardt-Cotting and Sunrow. Did you check if in your calculations you recover these relations or you violate them?
Yes, so in our perturbative calculations, we do satisfy the Burkhardt-Cottingham type sum rule, the BC sum rule. But there is a subtlety with the way you regulate the UV divergence. If you work with DimReg, then you can show that the sum rule does hold. As far as looking at the BC sum rule from lattice data is concerned, we also satisfy that, and that is what Krzysztof will be talking about in the next presentation. So in short, we do satisfy the sum rule.
Thank you.
Thank you, Shohini. If there are more comments, you can use the chat as always. And let's move to the last talk for this session by Krzysztof Cichy, who is going to talk about the lattice calculation of Twist-3 PDFs. Krzysztof, you may start. We cannot hear you well. Your sound is extremely low.
Okay, so maybe let me try to increase the... Is it better now?
There is
maybe
some
now?
background. If you keep it there, I think it's fine.
Okay. Yes, so do you see my screen?
Yes.
Okay, so I will not say much about the motivation for studying Twist-3 PDFs. It's clear from Shohini's talk. Let me just emphasize that even though they are kinematically suppressed, they contain a wealth of important information for the complete picture of the nucleon. And in the new experiments at the JLab's 12GeV upgrade and also at the EIC, we expect to obtain some experimental results for this. But nevertheless, this is difficult because of the kinematic suppression, and therefore any theoretical input is valuable, in particular from the lattice. So our work, the first part of our work was presented by Shohini. So this was the derivation of the matching formula. Since we cannot directly access light cone correlations on the lattice, we have to go to alternative methods. And one of them is the quasi-distribution approach, where you compute instead spatial correlations. And such quasi-distributions have the same infrared physics as your desired light cone distribution, and they differ in the ultraviolet. So you can compute the difference in perturbation theory and do the so-called matching. So in the first part of the work, we derived the matching formula for the Twist-3 PDFs. And now I will tell you about the lattice part, which was the extraction of the isovector combinations U minus D for the Twist-3 PDFs GT and HL. So first, a brief reminder of the quasi-distribution procedure. So as I said, we are probing spatial correlations in a boosted nucleon. So the first part is the lattice computation of Baire matrix elements. These Baire matrix elements contain logarithmic and power divergences, so they need to be renormalized. And for this, we use an intermediate Riemann scheme. And we also convert to another intermediate scheme, which is a modification of the MS bar scheme. And then these renormalized matrix elements can be used to reconstruct the X-dependence of your quasi-distribution. And from this quasi-distribution, you can perform the matching procedure to go to your desired light cone PDF. So the lattice matrix elements that we are computing are of the following form. So we have a boosted nucleon and an operator with a quark and anti-quark connected with a Wilson line and some Dirac structure. So for GT, we use the Dirac structure gamma 1, gamma 5, or gamma 2, gamma 5. For the Twist-2 helicity, so for the G1 distribution, this would be the gamma 3, gamma 5, where the boost and the Wilson line is in the 3 direction. And for HL, we use the Dirac structure sigma 1, 2, whereas sigma 1, 3 or sigma 2, 3 would be for the corresponding Twist-2 distribution. And then having the matrix elements and renormalizing them and inserting some kinematic factors, we can obtain the renormalized quasi-distribution and proceed with the matching. So our lattice setup is NF equal 2 plus 1 plus 1 twisted mass fermions with a Clover term and Iwasaki gluons. And the lattice spacing is around 0.09 Fermi. And we work here in this exploratory study at the non-physical pion mass, roughly twice heavier than the physical pion mass. Okay, so first the bare matrix elements, that there is not yet any physics in this, there are divergences, but nevertheless you can see here already some signs of convergence in the nucleon boost. So we employ 3 values of the nucleon boost from 0.8 GeV to 1.67 GeV, and ideally it should be converged in the nucleon boost to suppress the higher twist effects when going from the quasi-distribution to the light cone distribution. And for HL, the bare matrix elements show similar signs of convergence. So Shohini was talking about the matching, so I will skip this slide. And then I show you our results for GT. So this plot shows the dependence on the nucleon boost after the matching for our 3 boosts, and you can see that it's quite nicely converged. Within our uncertainties, we do not see any dependence on the nucleon boost. And we compared our GT to its twist 2 counterpart, which is G1, and you see that one of the features is that at low x, the GT seems to be larger than G1, but it falls off more steeply, and at some point it gets below G1. And as Shohini was announcing, we also checked whether the Burkhardt-Cottingham sum rule is satisfied. So indeed, this is satisfied in our data. The norm of GT is the same as the norm of G1 up to our uncertainties. And we also checked the Vanzura-Wilczek approximation, which states that the GT of X is fully determined by the twist 2 G1 of X, defining the function GT WW, which is an integral over only the twist 2 G1. The approximation is that GT is equal to this GT WW. And in this plot, I show you the GT WW from our data at 3 nucleon boosts. So these data only concern the function G1, the twist 2 function. And you see very nice signs of convergence here. There is no dependence on the nucleon boost. And then when we compare GTWW at the largest nucleon boost with the GT extracted from our data, so GTWW is in red or pink, and GT is in blue. So you can see that the WW approximation is indeed satisfied within uncertainties up to something like X equal 0.5. But and then it's a bit unclear what happens here. This region of X might be subject to systematic effects. But even in this regime where the WW approximation is satisfied, there is still possible violation up to something like 30 or 40%, because the uncertainties, especially for GT, are quite large. And interestingly, a similar possible violation quoted to be between 15 and 40%, depending on the X range, was found from experimental data in a paper already more than 10 years old by JLab. Okay, so now I move on to HL. HL contains this singular part in the matching, and we wanted to check what is the influence, the numerical effects of these singular terms on the matching. So in blue in this plot, you see the matching with all the terms included. And then in purple, you see what happens if we are excluding these R0 terms, which are here in brown or orange. And then in red, you see the exclusion of all the singular terms. And the conclusion is that basically you can see the influence only for very small x, smaller than something like 0.05. And this regime of x is not really reliable from the lattice at the presently achievable nucleon boosts. So the conclusion is that these singular parts only affect the very small x that are not yet accessible anyway. So it's not very important for our numerics, but theoretically, of course, it's important to understand the role of these terms, of these zero modes. And then we also made another check. So the standard procedure in the quasi-distribution approach is that we apply a cut at some value of xc, and we say that for q tilde of x with x larger than xc, the quasi-distribution is zero. So we wanted to check whether this assumption is important, and we tried to model the large X behavior of the quasi-distribution with perturbation theory inspired models of the form given here. So in blue, you see here our data for the quasi-distribution, the renormalized quasi-distribution, and two models of this form differing in the sign and the magnitude of C. And then doing the matching, assuming this large X behavior of the quasi-distributions, we checked what happens with the final distribution. And you see that here it's totally irrelevant what is happening at large X. So this procedure with a cut is totally justifiable. Okay, so then I show you the nucleon boost dependence of our HL. So again, 3 nucleon boosts from 0.8 to 1.67 GeV, and again you see very nice signs of convergence within our uncertainties. And then we compare the HL with its twist-2 counterpart, the H1, at the largest nucleon boost, and you see very similar qualitative features that at small x, the HL is larger than H1, but it falls off more steeply. Okay, so this brings me again to the Wanzura-Wilczek approximation, so this time for HL. This is the form of the WW approximation for this case. And again, here the conclusions are very similar as in the case of GT. So there is agreement between HL WW and HL for x smaller than around 0.55 within our pretty large uncertainties. But this still means still a possible violation of something up to 30 or 40%. Okay, so now my conclusions. So I would say the message of the talk is that there are some first promising results for the twist-3 PDFs GT of x and HL of x. That there is a preliminary physics result that the Wanzura-Wilczek approximation holds at least at small x, but there are still possible violations when taking the uncertainties into account. And of course, there's still a lot of work to make the studies more robust. This is only an exploratory study, and we need to investigate a lot of systematics that come both at the lattice side. So this is investigating the nucleon boost dependence, the pion mass dependence, since this was done at the non-physical pion mass, and also some standard lattice systematics like cutoff effects, finite volume effects, excited states in the matrix elements, and so on. And then there is other type of work that needs to be done, like there is this important question about the mixing with quark gluon quark operators, and also the role of zero modes, as well as the truncation effects in the matching, the higher twist effects, and so on. So it really needs a lot of work to make these results robust. But in the future, one can expect that lattice can provide some very important insight for this issue. Okay, so thank you very much for your attention.
Thank you, Krzysztof. I didn't even have the chance to give you my 2-minute mark. So we certainly have time for questions. Let me start by asking, do you think that you can use these methods of the quasi distributions to access Mellin moments? And do you think you can go to higher moments, and what you would do with local operators?
Okay, at this stage, this is unclear. So in principle, of course, you can do it. You can get the full X dependence. So in principle, you can get any moment. But in practice, indeed, the signal for the higher moments is not yet satisfactory. So in the future, yes, but right now, the signal is for the first, let's say, 3 moments, so something like this. So from this point of view, this approach does not yet beat the standard lattice approach of computing moments, but it has perspectives. So in the future, I believe it's possible.
Thank you. Okay, several questions. I think, Alessandro, you were first. No,
sorry.
John Ling.
Yeah, maybe just a simple question. In slide 10, why you discuss with and without R0? Is this R0 special?
Okay, yes. So it's a term. So Shohini was discussing this. There is the singular part of the matching kernel, and in this sense, that this is special. So we wanted to see what is the influence of these terms of numerics, in particular, which regions of X are mostly affected by these singular terms. They are related to these zero modes, and there has been a lot of debate in the literature about the zero modes. I'm not able to tell you any final conclusion or whether there is any agreement about the role of these zero modes. So it was just a numerical check where these terms are important. And it seems it's a very small x, which makes sense because the zero modes are related to the x equals 0 point.
Okay, thank you.
Alessandro?
Well, it's a similar question to Shohini's. Can you check in this approach if you fulfill Burkhardt-Cutting and sum rule, calculating consistently GT and G1 in the same way?
Yes, so this is what we did. We checked that, so we get the distribution and then we can integrate this distribution, and from this we get the same norm of these distributions, which is what the BC sum rule is telling us. Or are you asking something else?
No, it's really, I mean, that was the question. If you can numerically show the validity of the BC sum rule.
Yes.
Thank you.
Nabuo?
Hi, Krzysztof. I don't know if you have already done this, but one of the major murkiness in phenomenology for Twist-3, at least in the DIS case, is the interplay between the Twist-3 part and the target mass corrections. So, for instance, people from Hall A, for instance, the JLab, they have ongoing experiments to measure the D2 matrix element, because there are also lattice calculation, and they try to correct the data, using target mass corrections. So I know that you guys include target mass corrections into, your analysis. So I was wondering, if the signal, if you take the difference between the full GT minus the 1-0 Wilczek, how much of that difference comes from TMC effects? If you have that, or if you can do that, that would be very interesting, because it will give some insights of how we should proceed in phenomenology, because it's just basically too murky in practice.
Okay, yes, I agree. It would be very interesting, but we are not yet in position to address this issue. So it's still that. So we don't have the form of the target mass corrections for these distributions. But even if we have, so for the Twist-2 case, they are always small. So most likely here they are also not very huge, and I'm pretty sure they would be much smaller than our uncertainties that are pretty large, even the statistical uncertainties, and there is a lot of these systematic uncertainties. So I think it's not yet the level of precision where we can make any statement on this.
All right, thank you.
Okay, I don't see any raised hands, so let's thank Krzysztof and also the speakers of the session, which officially closes here. So thank you everyone for joining our session, and especially our speakers.
Sorry, I have a question.